Hi everyone, I'm Ben Miller and this is Life in the Fast Lanes. In this episode, I'm talking to Mike Beyers, product planner for Keysight's high-performance oscilloscopes, about the migration from non-return to zero, our NRZ signaling, to pulse amplitude modulation, PAM, our multi-level signaling. With the increasing demand for higher data rates in wired communications, NRZ systems are starting to show their bandwidth limitations. So pulse amplitude modulation has started to arise as a really popular alternative to that because of its higher data rates and spectral efficiency. However, there are some challenges involved with migrating from an NRZ signaling standard to a PAM4 signaling standard. I'll be talking to Mike about those challenges and how to overcome them, as well as all the different benefits of migrating from NRZ to PAM systems. So without further ado, I'd like to throw it over to Mike.
Hey, Ben. Yeah, sure. This is Mike Beyers. I am the Infinium product planner for Keysight Technologies. In particular, that makes me responsible for future product definition and application definition for Keysight's UXR series of oscilloscopes.
So let's just jump right into it. What do you think is the real challenge for using NRZ today, and why are standards moving away from it?
Sure. So, if we go back to the very beginning of high-speed serial with PCI Express Gen 1, it was 2.5 gigabit per second NRZ. And that required a 13 gigahertz oscilloscope. So we had lots of bandwidth relative to the baud rate that we were trying to push through a channel. As data rates have gone from 2.5 gigabits per second per lane on PCI Express, that I'm using as an example, all the way to the newest generation, PCI Express Gen 6, is 64 gigabits per second. So scaling that bandwidth, right, fundamentally the channel's not that different. So we're just not going to get the hundreds of gigahertz of bandwidth it would require if we kept that same ratio of bit rate to bandwidth. So we have to look for how to put a different way to put more bits through this fundamentally the same set of connectors.
And what's the difference between NRZ and PAM encoding?
Sure. Well, technically, NRZ is PAM, right? It's pulse amplitude modulation, but it's PAM2. It's two levels, right? We have one level for 0 and one level for 1. PAM takes that further and PAM4 uses 4 different voltage levels. PAM8 uses 8 different voltage levels. And so we use those extra levels to get more data using the same symbol rate. But there's a limit, right? That as we go to double the number of levels from NRZ or PAM2 to PAM4, we go from 1 bit per symbol to 2 bits per symbol, which is great. But if you go to PAM8, now you have 8 levels, but you only get 1 more bit, right? You quickly run out of signal to noise ratio, and as you try to use more and more levels of PAM in order to get more bits. So really, it's about channel cost, right? If we had optical or something, we could, we'd have many terahertz of bandwidth. But really, it's about that using more levels to shove more bits into the same baud rate. We don't want to go to more expensive board materials, more expensive connectors. We want to live with the same inexpensive channel.
So what challenges are engineers going to face as they move from NRZ to PAM in terms of signal processing requirements?
So increasingly, right, the baud rates are pushing closer and closer to the channel bandwidth, i.e. to that fundamental limit of how much we can get through a channel that's described by the Nyquist criteria. As we push closer to that, our eyes get closed, and more closed. And so we end up applying more equalization, more processing to be able to reliably extract the data bits out. Beyond that, we even after all the processing we do, it's still not perfect, right? So in the old days, right, we expected the transmission to be almost error-free. In today's world, often or almost always when we're using PAM encoding, we're pushing so close to the limit that not only do we have to use a lot of equalization to open the eyes and extract the data, but we have to use error correction as well. So the fundamental data error rate we're shooting for is no longer 1 e to the minus 12 or 1 e to the minus 15, but maybe 1 e to the minus 4, or in some cases 1 e to the minus 6, in some cases as low as 1 e to the minus 2, But error-free transmission is no longer the goal that we require, at least without the forward error correction, the FEC coding.
So are some of those challenges because of the increased sensitivity to noise that's inherent with PAM modulation?
Yes, right. It's really both those things together. Smaller signal height, more voltage levels equals a lot less spacings between our levels. But the other part is the eyes closing due to the channel bandwidth, and so there's a variety of equalization techniques used to try to recover that eye, to open that eye back up. There's FFE, feed forward equalization, typically used in the transmitter, but then also in the receiver. There's CTLE, continuous time linear equalization, as well as DFE, discrete feedback equalization, which is a nonlinear equalization technique. The advantage of the nonlinear equalizer, the DFE, is that it can open the eye without adding noise. One of the disadvantages, though, is that it's making the decision of what symbols are which correctly. So as you use long DFE equalizers, if you get one answer wrong, it can make the next answers wrong as well. And that poses a challenge for forward error correction. Forward error correction works great for randomly distributed errors. When you get bursts of errors, it can fail. So that's one of the things that we're looking for, is not only errors and how often the errors are in the traditional bit error rate, but also anytime there's bursts of errors that can lead to FEC failure, or what we call frame loss. It's no longer bit error rate, but it's frame loss or frame loss rate.
So does that lead to some of the timing and synchronization issues with PAM?
Yeah. So if we think about jitter, we've been talking about the closure of the eye vertically, but jitter is the closure of the eye horizontally, which is still a challenge, as we're talking about 32 gigabaud signals and above. Jitter fundamentally has two contributions. There's intrinsic jitter of a signal that is due to, say, the clock. Then there's the jitter due to noise, and that the faster the slew rate, the less the noise matter, right? That second contribution is really the noise divided by the slew rate. So if we had infinite slew rate, it wouldn't be a problem. But again, because we have limited bandwidth, we have a limited slew rate, and so therefore, this noise over slew rate contribution, especially in PAM, is becoming an increasingly important part in comparison to the intrinsic jitter that we found mostly in NRZ. Normally, when we talked about jitter, we thought about jitter separate from noise, but now we have this new component of jitter in our PAM signals that we really need to think about much more about the noise and the signal noise ratio in our systems.
Mm-hmm. So how do the test and measurement challenges differ between NRZ system and a PAM system?
Let's talk about the evolution of the specifications. Well, the old way we used to make jitter measurements was apply a defined equalizer, a reference equalizer inside the oscilloscope, and then make the jitter measurement on the open eye. But in today's world, the specification doesn't want to talk as much about exactly what the equalizer is. And so they require the jitter measurements to be made on the signal without equalization applied, i.e. the closed eye. So how do you make jitter measurements on a closed eye? Or noise measurements on a closed eye. And these are some of the new measurements you find for PAM, including 12-edge jitter. We call it 12-edge jitter because we're measuring at 12 specific places in that waveform. If you think about it, we're going to start from a 0, 1, 2, 3, and we're going to go to, one of the other three symbols. So there's 12 possible transitions, right? 0 to 1, 0 to 2, 0 to 3, et cetera. You go through all the possible combinations. There's 12 possible combinations. And we've called out in the specification 12 specific places in that pattern that we're going to make this jitter. So that's how we make that jitter measurement on that closed eye. And then also from a vertical noise perspective, we also make SNDR measurements. So SNDR has been around a long time for analog signals, where you put in a sine wave and then you measure what you get, the best fit sine wave versus the noise and distortion. But this is SNDR relative to a digital pattern. Very much the same techniques, but really it's a new way of being able to measure the noise and distortion. Both matter, right? Because we're talking about a linear output on a closed eye.
So let's talk a little bit about some of the standards that are using PAM today. Could you tell me what those are? And do you think it's going to be a trend that more and more standards are going to be adopting PAM in the future?
Where it started was the very fastest signals, the Ethernet signals, the IEEE 802.3CK on the electrical side, and a lot of equivalent on the optical side. That's a 53 gigabaud PAM4 signal for 100 gigabit per lane, i.e. 400 gigabit Ethernet. We've also already mentioned PCI Express Gen 6 is moving to PAM4. USB is moving to PAM3 with USB 4 version 2. Beyond that, various DDR and MIPI standards are also talking and starting investigating, moving to either PAM3 or PAM4 type symbols or signals. And then last but not least, there's a variety of research going on where people are looking at even PAM6 and PAM8. We don't have any specifications calling those out quite yet, but those are supported in our UXR-B software if you're in that arena. Last but not least is the coherent optical communication space. It's completely different in the sense that it uses quadrature amplitude modulation, QAM, which is really PAM in both the vertical and the horizontal axis. So if you have a PAM4I and a PAM4Q signal, that creates 16 different possible combinations in quadrature, and that's QAM 16.
So what are some of the key specifications or requirements that you're going to need for an oscilloscope when you're doing that testing?
Sure. Good question. So I think first and foremost is bandwidth. Right? We've talked about trying to push an increasing amount of data through the same channel. So you need enough bandwidth to see the output of the transmitter. Take, for example, the next generation Ethernet standards at 112 gigabaud PAM4. That'll require an 80 gigahertz oscilloscope to view. So the UXR-B best-in-class bandwidth up to 110 gigahertz can cover the most demanding standards. But beyond that, the jitter, the noise, the things that close our eye horizontally and vertically are increasingly important, right? The intrinsic jitter of an oscilloscope. And, an oscilloscope has both a noise-induced jitter and an intrinsic jitter component, just like the transmitters. And the intrinsic jitter component of the UXR-B is 15 femtoseconds RMS, so incredibly low. As well as best-in-class noise, right? Because especially as we're dealing with closed eyes, and whether or not we're applying equalization, we're looking at the end of a very lossy channel. So there's just not much signal left. So not only having enough bandwidth, but having a low enough noise to be able to make those measurements. Last but not least, even with the best-in-class oscilloscopes, these measurements are a challenge. So increasingly, we look to compensate the noise of the oscilloscope. It's always best to start with the lowest noise, widest bandwidth scope you can get. But also then, when it comes to the 12-edge jitter measurement, the SNDR measurements, we can try to compensate for the oscilloscope contribution to that noise, to back out a bit of that contribution and get the customer some more test margin. It's really an emerging measurement science area, and it's an area where you're going to want to definitely get the most recent revision of the software for your Infinium oscilloscope, because we're constantly making improvements on that. The UXR-B has the bandwidth necessary for the highest, most demanding standards, the lowest noise, the lowest jitter, to give you the most test margin on both your vertical measurements like SNDR and your horizontal 12-edge jitter measurements, as well as the most recent, most advanced measurement science to compensate for the noise of the scope, as well as have the processing speed to make the measurements, these increasingly complex, increasingly demanding measurements in well, a reasonable amount of time.
Thank you again to Mike for his time today. As you can tell from our discussion, the industry trend toward PAM signaling is not going to end anytime soon. So it's extremely important for developers and designers to learn how to design, measure, and test using multi-level signaling, and have the right tools to do so. If you have any questions about how to do that or about signal integrity in multi-level systems, check out the resources below. Until next time, this has been Life in the Fast Lanes.